So hello everybody, I'm Enrico. I'm a tech lead in the distributed systems team at Yelp. I work mostly on streaming architecture, and I've been working on the Kafka deployment and logging infrastructure at Yelp. And in the last year, so most recently, worked on the Apache project at Yelp. Today I'm going to talk about how we use Flink to power the data pipeline infrastructure. First of all, for who doesn't know Yelp, this is our mission statement. We connect people with great local businesses. About today, I'm going to start by giving you an architectural overview of our data pipeline infrastructure, and then I'll focus on some use case that can highlight the limitations and challenges that we were encountering last year before introducing Apache Flink, and then how Apache Flink helped us solving those problems. Finally, I'll talk about how we introduced Apache Flink into an existing infrastructure at scale, and then how we currently do deployment. Let's start with some historical context first. We really started some streaming back in the days with Scribe. Scribe used to be an open source Facebook project. It's mostly used for log aggregation. That's what we were using it for. We were running a Scribe leaf on every host in the infrastructure, and then streaming data on some log aggregation servers. Then on the servers, we literally had a tail-f, tailing the file that was getting written, and then streaming the content on an OpenTCP socket for the consumer application. Basically, there was no actual consumer interface. This actually allowed us to do some very, very primitive stream processing. We started looking at more advanced use cases, and we tried to introduce Apache Storm, but the project internally never really took off. The problems were probably like about the underlying infrastructure, and also the interface wasn't really a good fit for our use cases. So we decided to actually refactor the way we were doing streaming by introducing Apache Kafka. That was really a game changer. We now finally had a consumer interface. We could checkpoint the state of processing by committing offsets. We could scale by adding more partitions. We could also replay logs by just replaying the content of a topic. So that allowed us to start building more applications on top of it. And we introduced the data pipeline infrastructure shortly after. We started also doing some Spark streaming processing that we still do today. This is more like micro-batching streaming applications. And then finally, last year, after coming to the Flink Forward conference, we started looking into Flink to solve more advanced streaming applications. I talked about data pipeline. This is what I see being like a data pipeline architecture stack. I think the fundamental block is a streaming engine. To be able to build a data pipeline, you need something that provides you with a producer-consumer interface. And then once you have that could be Apache Kafka or any other product out there. But once you have that, now you build on top of it, and you need a way to actually serialize and transmit the data into the infrastructure. So you start looking at a serialization protocol. That can be Avro, so binary protocol, can be text-based like JSON. If you just use the protocol, you can't really represent the data that you have in the data pipeline. So that's what you need a schema for. The schema allows you to actually represent the data that is flowing into the infrastructure. And to be able to actually discover the data, you need a registry. So you need a schema, and you need to be able to register those schemas into a schema registry. Once you have those three fundamental blocks, you build on top of it. You need data sources so that you can start streaming data into the infrastructure. Data sources is anything that basically produces events. Once you have data flowing, now you want to do something with the data, some analysis, and then when you start looking at a stream processor to do stream processing, implement applications, and usually very coupled with stream processors are data sinks. Data sinks allow you to get data from a stream and to ingest the data into a different data store that doesn't provide a streaming interface. But can be used for online or offline analysis. At Yelp, this looks like this, where our streaming engine is Apache Kafka. So it powers the entire pipeline. And then we have Avro as a serialization protocol. And our schema registry is an HTTP service that we developed in-house, and it's called the Schematizer. It does much more than just being a simple schema registry. It actually controls, it's sort of a centralized brain that controls the entire infrastructure and pretty much connects all the moving pieces. The data sources, we have a variety of them, MySQL, any web service. And then from the stream processor side, we run Flink, some stream SQL jobs, and we also have some Python flat map. This architecture is recursive on the processing side because data that is being processed can go back into Kafka. And then eventually, on the right side here, we have the data sinks. They form what we call connector ecosystem. Basically, we can move any data from any stream into one of these data stores, or any new data store that we may need in the future. So I want to start talking about the data sources first. We can distinguish between two main data sources at Yelp. One is what we call a log event. This is generated in the context of any web request is usually online. And the properties are that it's usually very low latency. So imagine that we produce hundreds or thousands of these events per web request. So this needs to be super fast. It's very high throughput, and the way this gets implemented into a Kafka topic is by using very highly partitioned topics. It's usually unordered, and we are generally okay with having data loss or data duplication. It's like a trade-off to have a very low latency. Because we mostly run Python services, we can't really leverage multi-threading. That's why we actually deploy this local daemon that we call Monk, that is used by application to offload the actual message production into Kafka. The second data source that we have is what we call data store changelog. This is mostly offline, so we have our web service that is interacting with a data store. It can be MySQL, for example, for some reason, because the web service may actually need to use MySQL. And then we have a separate service that we call replication handler that listens to all the changes that are happening to the tables in the data store, and we replicate those changes into Kafka. The idea here is that at any point in time, we want to be able to replay the entire Kafka topic and be able to reconstruct the originating table. Usually here we have a single partition topics because we need global ordering to actually be able to then reconstruct perfectly the table at the end. And we need to support the basic operations that we have in a data store, so insert, update, and delete. We usually use compacted topics that are compacted using the primary key of the originating table. Once we get the data flowing in the infrastructure, we actually started building some data sources. We actually started from the MySQL one, then we introduced the log events, and we needed to provide our users with a way to process the data and leverage the data. And that's when we actually started looking at stream processors. Because we mostly run Python, we needed to give away an easy way for developers to do stream processing, and we looked into Python. So we built what we call the paastorm, that is a Python stream processor. The name comes from our service platform that's called Pasta, and Storm, because the primary operator is basically inspired by a fusion between a storm spout and a bolt. What this is, in the end, is just a thin wrapper around a Kafka consumer and a Kafka producer. And the idea here is to abstract away the details, the underlying details of the Kafka infrastructure from the user. So the interface for users is they need to specify input streams by specifying the input schema, and output streams by specifying the output schema, and then finally they need to implement a process message function. Our infrastructure is very schema-centric. Users are never really exposed to topics or partitions or Kafka clusters. They reason about the schemas, so that's the way they discover data. This framework can be scaled. It relies on Kafka Consumer Group for scalability. And in general, this is a good fit for simple flat map operations, especially when you need to use a Python library that has already been implemented and users are familiar with. But there are more advanced applications that are actually pretty hard to implement in paastorm. I'm going through two use cases. that can really highlight what were the challenges. The first one is part of the connector ecosystem that I mentioned before. It's called Redshift connector. It's a data sync. The goal of this application is to get data from a stream and ingest the data into a Redshift cluster without introducing any data loss or duplication. If you think about this system, the way we actually implemented it was by organizing it into a sort of a two-stage architecture. The first stage, that's what I call here S3 processor, will batch the messages from the stream as they arrive, batch the messages locally, and then once we reach at a certain size or a timeout, this will upload the messages into S3 bucket in CSV format. When we upload, we use a unique key because we don't want to introduce any duplicate, so we need to work around S3 eventual consistency. So we use a unique key. We also send a message through the second stage of this pipeline with the key that we use to upload the file, and also the offset information. In case of failures, the S3 processor will reuse the same notification message to recover the latest uploaded offset. The second stage is called Redshift loader. We look at the key from the notification message and use the copy command to upload to Redshift. So we implemented this in paastorm. These were two spots, two distinct applications. But we actually encountered a lot of challenges into making the first stage work, especially around scalability and probably lack of proper interface. In paastorm, the only thing that we had was a process message function. So we couldn't really, there was no actual abstraction for accumulators, windows, or triggers. So yes, you can implement something like this, but the code is clearly not really nice. It can become actually really, really complicated, which means difficult to maintain in the longer term. Also, because when we started ingesting hundreds of topics, we started seeing a lot of challenges scaling these applications, because every time there was some failure in the Kafka infrastructure, or something like an instance going up, leader change in a topic, this would cause trashing of all the buffered data because the consumer group was going to rebalance. The second use case is the unwindowed join. In this application, we get streams that represent MySQL changes, and we want to join those streams over a join key. This is a pure stateful application. You basically retain the state forever. There is no window. The only thing limiting the size of the state is really just the number of distinct keys that you have in the incoming streams. In this case, if you imagine this application, you have two streams coming with different keys. You need to store each value for each stream. Each stream will be a component of the join, so you need to store each value for that component into the state. Once you have all the components, you can emit a join message. Because these are actually representing MySQL changes, you also need to be able to represent delete messages. So if you receive a delete message from one of the components, you need to remove the corresponding value from the state and emit a delete message to signal that something was removed from the join. Here the challenges were mostly related to state management and scalability again. First of all, we tried to implement this in paastorm, and we started implementing state management from zero. It's actually pretty hard. And most of the issues we encountered were around corrupted state, and also how to checkpoint the state when you don't actually have a real distributed runtime. This application was basically impossible to scale also, because we needed to join different streams. So we wanted the streams to all go to the same process, and there was a single Python process. We were basically not using the Kafka consumer group at all. We couldn't use it. So what we realized was that we had a lot of value in our streams in Kafka, but we were not fully using all of the value. And we needed powerful tools to actually be able to extract the value from the data. That's when we started looking into Apache Flink. For me personally, I really like the abstraction of the streaming primitives. With Apache Flink, we could use windows, triggers, map, flat map. If you combine them, you can theoretically solve all of these streaming problems that you may have. Also, one thing that we really cared about our framework for paastorm was the abstraction of the streaming engine. We don't want user to care about Kafka, to know anything about Kafka, the underlying Kafka infrastructure. And you get that from Flink, because in the end, users work on a data stream. The way you create a data stream is really just an infrastructure concern. Then obviously state management out of the box, and finally we could do event time processing that we couldn't do before when we were using paastorm. And then with Flink we could actually scale without being coupled with the number of Kafka partitions. So the two applications I showed you before in Flink, they are, the first one, the connector, is really a global window with a custom trigger. The custom trigger will fire based on number of batched messages or timeout. And then once we actually, on the global window, we run a fold function that will accumulate the data, and then when the trigger fire, it will upload the file on S3. And finally, send a message to a producer sync to notify the second stage of the application that stays implemented in paastorm, because really the other stage is not really doing any particular stream processing. It's actually pretty simple. The window join that was actually the hardest to implement in paastorm was here. It's probably the simplest, I believe, because in the end, we leverage the operations over data streams. The union operator allows you to merge together a bunch of data streams and provide that as a unique data stream to the underlying, to the downstream operators. So once we union the data streams, we use key by to key based on the join key. And now we can use a rich flat map function with a map state to store in the map state. The key will be the incoming component of the join, and the value will be the value for that component of the join. Once in the map, you have all the components, the value for all the components, you just emit the join message. And obviously, state management is already provided by Flink itself. We actually went even further with streaming SQL. When I say even further, I mean we didn't just abstract the streaming engine, but also the stream processor. Because in the end, with stream SQL, users don't really need to know the specifics of Flink. Potentially, they don't really need to know that there is Flink running. They just need to write a stream SQL. We provide this as a service. So users submit a config file, a YAML file, and that looks more or less like this. And then we run the job automatically as soon as they submit the file. Here they have to describe input streams for their query, output streams, and then whether they want to use event time or processing time. And finally, the body of their query, that is, in the end, their processing applications. We allow users to also define UDFs that we can run for them. Initially, I was talking about the connector ecosystem. For us, connectors are really a fundamental part of the infrastructure. A lot of times, actually, users just get data into a data pipeline so they can have a uniform way to then ingest the data into a different data store. We built this ecosystem trying to really build components and applications that are highly reusable. And in general, we want all the connectors to be generic so that we implement it. If we have one use case, we want to get this data into this data store, for example, Cassandra, we build the connector once for that specific data, but that connector should actually be able to be used for every data going through the pipeline. From an implementation point of view, this looks more or less like Flink applications that have a Kafka, the source, and then they implement a Flink sync specific to the destination data store. We have a pretty strict set of specifications for connectors that can be considered data pipeline compatible. First of all, they can't really do any transformation, just minimum transformation necessary to make the connector compatible with the destination data store. And then they have to support a minimum set of Avro data types so that they are actually reusable for any other data. And then they must come with an auditor. The auditor is actually really important here. If you can't trust the ingestion process into your data store, you can't trust the data that is in the data store at all. So imagine you're getting data into Redshift because then you want to use the data to train a machine learning model. If you can trust the process that gets the data into Redshift, maybe there is duplicates, data loss. How can you trust the model you just trained? So for us, we have these auditors. The auditing process is mostly offline. It verifies data loss, duplication, and whenever applicable, consistency and ordering. It usually works by comparing chunks of data from the Kafka topic with the data into the destination data store. As part of the connector ecosystem, we try to make the interface with connector as consistent as possible for both maintainers and users. So setting up a data connector for a new schema, so for data is pretty simple. That's what we call data connection. It creates this link, and users just use a command line tool. And from a maintainer point of view, that gives you a consistent architecture to reason about when you actually have to develop and maintain these systems. When you put everything together, you end up with something that looks more like a processing graph, where the edges are Kafka topics, and then most of the processing tasks are implemented in Flink. So here, for example, we may have data coming from a MySQL table, data store changelog, or a web service. The MySQL gets transformed by a Python flat map transformation and gets data into Kafka, and then gets joined with the first source by a Flink job, and then maybe the data gets ingested into Redshift by the Flink Redshift connector, or maybe it gets processed by a string SQL, and finally get into Cassandra, always using a Flink-based connector. If I think about last year, we really didn't have any Flink running. We didn't even have Java or Scala libraries to interact with the data pipeline. We now have Flink applications powering business-critical applications. And actually, a few weeks ago, during an hackathon, we managed to get users who had never used Flink up and running in less than a couple of hours. And their applications were already integrated with the rest of the infrastructure. I think there were two properties that proved to be really valuable on the road to actually run Flink. The first one is a very strong standardization starting from the message envelope. Early, while designing the data pipeline, we decided to get all the data, so the user payload, encapsulated into what we call message envelope. The message envelope is Avro-encoded and contains internally the Avro-encoded user payload. Having an envelope allows us to be very flexible and extend the data that is flowing through Kafka with infrastructure attributes, and we may need to introduce new applications at any point in time without actually having to change or impact the consumer application. Especially when you want to build reusable components, I think there are a few attributes that are really important. One of these is definitely the event time. We have a standard format. Users cannot control that. They can control the value in some cases, but they can't change the format. That allows you to, for example, extract the timestamp in one way across all the Flink applications. You implement it once, it applies everywhere. Similarly, you can reason about the watermark unit in Flink. The second attribute here, the message identity, is actually pretty important for auditors because given a message, that allows to know exactly where the message is coming from in Kafka. In the end, what Flink needs to be able to do in order to interact with the rest of the data pipeline is just serialize and deserialize the envelope. The second property is a very centralized data discovery. All of the data is available in our schema registry, schematizer. Flink, to be able to serialize and deserialize and understand the user data, needs to talk to schematizer, retrieve the schema, and then the schema can be used either for consumption or for production. But schematizer does more than that. It also provides the actual data, physical location of the data. So Flink would interact with schematizer when building the topology to configure consumers and producers. And because we can we run a multi-regional deployment for Kafka, data can live in one or more Kafka clusters. We need to be able, for Flink to be able to consume the data from everywhere. The schematizer also provides the abstraction for the allocation of topics in addition to discovery. So also for production, Flink needs to allocate any schema through the schematizer. As I was saying, because we run a multi-regional deployment, one thing we did to be able to consume aggregated data was leveraging the data stream union operator. This was actually a pretty great way to enable applications to do aggregated processing of data without having to do anything more than just writing a couple of lines of code. I think this solution is pretty good to get started, but then if you want to do something more complicated on event time, your application can start suffering from the reading a different latency from different clusters. So something that we are actually looking for the future is trying to pre-aggregate the data into an aggregated Kafka cluster. Finally, I'm going to talk now about how we run Flink. I think our deployment is actually pretty young. We started with Flink 1 year ago, running in production, I think, probably for 9 months now. So definitely, I think also we focused a lot on building new applications and probably less on the deployment side of the story. One choice where we made was running Flink on AWS EMR. And I think this was a great way to get us started with the technology while not having to learn how to run a Yarn cluster or how to maintain an actual Flink cluster or even trying to integrate Flink with the Mesos deployment that we use for services. So we could basically focus on building applications. We could do that because we had an in-house tool called Cascade that allows us to launch and easily manage EMR clusters. When we run Flink, we usually run 1 EMR cluster per Flink application. And in the case of connectors, we prefer to have very small topologies to large topologies. So for connectors, we would actually have a small topology made of a source, map when necessary, and a data sink for each connection. And that will be just a single job. So we end up running hundreds of jobs into the same Flink cluster on a single job manager. This obviously provides better isolation than running a huge topology that consumes from all the streams, so that failures in one of the streams doesn't bring down the entire topology. So it's actually a pretty good way to run this, to run our connectors. However, if we moved away from EMR into something that is more like Mesos or Kubernetes, we'll probably start looking into actually run a single Flink cluster with a dedicated job manager per connection, so per job. To be able to run hundreds of jobs, we had to develop something that we call the Flink Supervisor. It's a long-running Python process that takes care of managing the Yarn session, launching the Flink cluster, running all the jobs whenever we need to run them, restarting the job if they fail, alerting whenever a job is not coming back up. It also manages the checkpoints and save points. It actually stores the path of the checkpoint and save points into a persistent location in DynamoDB that allows us to recover every time we want to redeploy a cluster or across job failures. We don't run Flink in HA mode, so we don't have the checkpoint metadata information in Zookeeper. For this reason, we can't really rely on S3 path because list operation in S3 is not consistent. So we store the path on S3 on DynamoDB, and that's where we recover it from in case of failures. Around the state management side, we use RocksDB within incremental checkpoints and only use externalized checkpoints. We actually found some issues around serialization of the state. When we changed some of the classes that were part of the state, our base class that is called message class, we ended up with a non-backward compatible state, and migration was actually really hard. So what we ended up doing now is we have a custom type serializer that serializes the state, everything that is in the state, especially the message class in Avro, and prepends a magic byte that is used to perform state migrations every time we need it. To conclude, these are our current run numbers around Apache Flink. We mostly run 1.3.2. We are in the process of upgrading to 1.4. Yeah, so these are actually our engineering social media channels. And obviously we are hiring, especially if you're interested in stream processing challenges, you can come talk to me later. And I can take any question now. Yeah.
What's roughly the state of the size that you're dealing with?
The what?
The state of the size. I mean, size of the size of the state.
Yeah, the state size. It depends on the applications. For example, the Unwindowed join can have a state up to few tens of gigabytes usually. It could also be bigger than that, but I think right now the Unwindowed join is probably the biggest size that we have. So tens of gigabytes, I would say.
I'm curious, as like mostly Python shop, do you give sort of any libraries that help people write the Scala or Java code in Flink better, or is it mostly? I'm just kind of curious what the division is between SQL versus, straight up normal Flink.
Yeah, so we have mostly, I would say, three kind of applications today. One are connectors. So for connectors, we build them in Scala. Just because they are very reusable. So once you build it once, it will work on everything. You don't really need to change it apart from maintaining the connector. Then we have stream SQL jobs. So that will be the abstraction on top of Flink. For interacting with Python software, we just recommend users to use paastorm for now. And that's okay if they only want to do like simple transformations. For something more complicated, we will end up recommending writing a custom Flink app. So they will be using the data stream, the streaming API on top of Flink.
Thank you for your talk. It's really interesting. At Zendesk, we want to introduce Flink into production as well, and I struggled with make the cluster really stable. We're on Kubernetes. Typical error, like I see task manager is killed or lost. So do you see some similar issues when you play with Flink?
I would say running on EMR, I mean, we obviously saw some challenges into getting to a stable deployment. Usually, the challenges are around properly sizing the task managers or around making sure. We did some tuning around memory utilization. For example, one thing we did when running on EMR, we actually disabled the Yarn virtual memory and physical memory checks. So the Yarn will never kill a task manager. And for us, that's okay because the EMR cluster is dedicated for Flink. So it's not like multi-tenant that we run Spark or other things on top of it. So I prefer actually to be the OS killer, to OM killer from the OS to actually kill the task manager rather than Yarn. Yarn is very sensitive. So that was actually one issue we encountered when running it on EMR.
Thank you. Sorry, one more question about the DynamoDB state management. So did you write some customized DynamoDB backend so you can
So
write
we don't store the state in DynamoDB. We only state the checkpoint path on DynamoDB. The state is stored on S3. But the problem we have is that we need the checkpoint path to be able to recover from the state. And that's what we store on DynamoDB. Because potentially you can say, okay, I can list the content of my S3 bucket and see what's in there. But the list operation on S3 is not consistent. So you may find the path there, you may not find it. That's why we actually use DynamoDB. It's mostly to have a consistent view of all the checkpoints that have been taken.
Thank you.
I have a question regarding the Avro. Mm-hmm. So you said there are changes that you make to the Avro, and that seemed to work fine. And like when you make changes, how do you do the rollout, especially when you have a value that may be dependent on the old one?
So I think this is regarding the envelope.
Yeah, the Avro serializer that you had, and you make changes to that.
So we don't make changes to the Avro serializer, really. What we do, we encapsulate the user payload into another, that is an Avro serialized, is Avro serialized data into another Avro serialized data that is the envelope. So what we can modify is the attributes in the envelope while maintaining backward compatibility and without impacting the user payload.
Thank you.
Excuse me. So less of a technology question. How did you go about kind of convincing teams to adopt Flink? Meaning, like, how are teams divided at Yelp, and how do you tackle organizational challenges and convincing people that this is something that they should do?
It really depends on the use case. In some cases, it's easy because they don't have other ways to solve their problems. So if teams come to me and say, hey, we need to do this very complicated window of aggregation, and then we need to compute this, this, and this, I usually say, okay, you don't have other options. You can't really do this in other systems, not even Spark streaming. Especially if you're using micro-batching. For example, all of our connectors, we couldn't implement them in any other technology. Probably in paastorm, that would have been like really, really hard. In some other cases, I think the major roadblock is really convincing people to use something different than Python. With Stream SQL, it's a little bit easier because you present them a nicer abstraction, and on top of that, we tell them, hey, you just write this query and we run it for you. We maintain the query, we maintain the job for them. Whereas if they were running in Python, we would say, hey, then you need to actually maintain your service. So that's one strategy. However, you can't solve everything with Stream SQL. So in those cases, more of an open challenge, I would say.
A question about envelope format that you're using. Did you consider using Kafka headers instead of this kind of another Avro encoding of the message?
So when we started building this, there were no Kafka headers. So the problem I see with Kafka headers is that they are coupled with Kafka. So if at some point, let's say you want to change your streaming engine, you have the coupling with Kafka. We still probably have other parts of the pipeline that have some sort of coupling with Kafka, so it's not like tomorrow we can just go ahead and replace Kafka with something else. But in this case, headers were not available, so we couldn't use them while building.
Pretty happy with your choice, basically.
Sorry?
You're pretty happy with your choice.
Yeah.
Okay, I'm afraid we're running out of time, but I'm sure Enrico is happy to answer questions
any offline
at lunch or here. So let's thank him again, please.